As we continue our study of microorganisms, we're going to have to talk about how they grow and how they reproduce. All of these things are going to require energy. And chemistry is something we need to know so we can talk about how organisms produce energy. Matter is made up, everything is made up of matter, and matter is anything that takes up space and has mass. Mass is sort of like weight. If you're a physicist, the difference between mass and weight is a big deal, but for our purposes, mass is weight. Matter exists in three forms. We have solids, liquids, and gases. The distance between the molecules that make up matter is what determines whether they are solids, liquids, or gases. If there's a lot of distance between the molecules, they tend to be gases. If there's not a lot of distance between the molecules, they're solids, and liquids are somewhere in between. All matter is made up of atoms. So let's look at what atoms look like. Atoms have many subatomic particles, but there are three major ones that we need to talk about. The first one is the proton. Now, protons have a positive charge. They have a mass of 1, and they reside in the nucleus or the center of the atom. Neutrons are neutral. They have no charge. Neutron and neutral mean pretty much the same thing here. They too have a mass of 1, just like the protons, and they also hang out in the nucleus of the atom along with the protons. Electrons have a negative charge. Now, they have technically no mass. They have a little tiny bit of mass, but really technically no mass. We need to start thinking about electrons as though they are little tiny bits of energy, because where the electrons go is where the energy goes. And when we talk about cellular metabolism, it's all about energy. The electrons move around the nucleus in pre-described areas that are called orbitals. This is one of the simplest of the depictions of an atom. You have the protons and the neutrons here in the nucleus, and then the electrons are shown going around in these nice, neat little circles. Electrons don't travel in nice, neat little circles. You need to think of the electron path as being more like bees buzzing around a flower. The only difference is with these bees, if they're in this energy shell, they stay this distance from the nucleus. If they have a little more energy, they're a little further out and they stay this distance from the nucleus. So they're not traveling around in nice, neat little circles, but they're kind of buzzing around inside this shell. Now, the basic pieces of matter are called elements. Elements are composed of one kind of atom, and here we have a periodic table of the elements. There are 93 naturally occurring elements, and then there are some elements that have been kind of made in test tubes that make up the remainder of these elements are shown here. Notice how each box has a unique number in it here at the top, and each box has a unique set of letters in it. No duplications here. These are the chemical symbols, and some of the chemical symbols make sense, like hydrogen is H. Some of them don't make as much sense, like sodium is in A. That's because they sometimes reverted back to Latin words. The Latin word for sodium is natrium, N-A-T-R-I-U-M, so now Na makes a little more sense. Now, elements, as I said, are composed of one type of atom. And here's just a little piece of that periodic table so we can talk about what some of these numbers mean. This is boron, carbon, nitrogen, and oxygen. So they all make complete sense as to why those letters are the chemical symbols for those elements. All elements differ from one another in their atomic number, which is this number in the top of the box, 5, 6, 7, and 8 in this instance. If you can go back to that periodic table of elements, you'll see that every single box has a different number in it. There are no duplicate numbers. Now, the atomic number tells you how many protons are in an element's atoms. The number at the bottom of the box is the atomic mass. This is how much mass the one atom would have. Now, because they get this from averaging a bunch of atoms, they don't always get a whole number. So we always round up. So here in the case of boron, this would be 11. In carbon here, it would be 12. Now, the two things that contribute to the mass of an atom are the number of protons and the number of neutrons. So if you know boron has 5 protons and an atomic mass of 11, 11 minus 5 means it has 6 neutrons normally. You can also tell how many electrons an atom has because atoms have to be electrically neutral. So it has to have as many positive charges as it has negative charges. So the number of protons and the number of electrons are equal. Carbon has 6 protons and 6 electrons. Compounds are composed of 2 or more kinds of atoms, and most of what we deal with in life are compounds. Now, molecules get a little tricky. Molecules are 2 or more atoms held together by a chemical bond. A molecule is the smallest part of a compound that will tell you what's in that compound. Here's 2 or more different kinds of atoms, and the subscript number tells you how many atoms of each element are in there. So we have water and carbon dioxide and glucose. And since this is 2 or more different kinds of atoms held together by chemical bonds, these molecules represent compounds. But elements may sometimes chemically combine with each other, and you may have molecules of an element. Hydrogen, for example, will bond, one atom of hydrogen will bond with another atom of hydrogen. That's a molecule of hydrogen. So it is possible to have molecules of elements. You need to see, is it 2 or more different atoms? That's a compound. Is it just 2 atoms or 3 atoms that are the same? That's still an element, but it's a molecule of an element. So let's talk about chemical bonds. And to understand chemical bonds, you have to know a little bit about valence. Valence is the number of electrons in the outermost shell of any atom. And it is this that determines how chemically reactive the atom is, what it will combine with, and how it will combine with things. Atoms combine with each other in order to fill the outermost shell. All atoms are seeking to have a full outer shell of electrons, and they combine with other atoms to make that happen. Atoms are stable if there are 8 electrons in their outer shell, with the exception of the first shell. The first shell will only hold 2 electrons, and after that, each outermost shell has to hold 8 if it's full. Now, there are all kinds of subshells under these shells. We're not going to worry about that. We're just worrying about that outermost shell has to have 8 electrons, and then it's chemically inert, meaning it won't combine with anything. So here you see an atom, 2 electrons in the outer shell. That is completely happy. That atom will not combine with anything. Here you have 8 in the second shell that's full. This atom will not combine with anything. Now, this atom really looks like this. It's still got its inner shell of 2, and then its next shell out is 8. And if you go a little further, there would be another shell, and it would have to have 8 for the atom to be chemically inert. So here is just a little piece of that periodic table with just those protons and electrons showing, and it shows here in their shells. So you see hydrogen just has the 1 electron. Helium over here has 2, so it's full. As we go along here, all of the inner shells have 2 because we build on top of that basic structure. And then we have 1, and then we have 2, and then we have 3, and we have 4, 5, 6, 7, and finally 8. Any of the elements in this last column over here are what we call chemically inert. They have full outer shells, they don't want to combine with any other atom, and they won't combine with any other atom. Helium, they use helium in kids' balloons all the time. Helium is lighter than air, and it's chemically inert, so it won't burn, and that's why it's so safe. Neon is used in a lot of signs. Why? Because you can pass an electrical current through it, and it will glow but it won't burn, it won't do anything, it's chemically inert. But all the rest of these atoms over here are seeking some electrons somehow or the other so that they can have full outer shells. So let's look at the different types of chemical bonds. We have a couple of really strong bonds, and those are the covalent bonds and the ionic bonds. And then we have sort of a chemical attraction. It's not quite a bond, but it causes atoms to stick together. It causes molecules to stick together, and those are the hydrogen bonds. Let's say you have two pieces of paper and you want to keep them connected together. You could put a staple in them, and that would take a lot of energy because you'd have to push on the stapler and hold that together. And then if you wanted to get the two pieces of paper apart, you'd have to find that staple puller, and that would take a lot of energy. Ionic and covalent bonds are like that. It takes a fair amount of energy to make them. When you break them, you release a lot of energy, so they're very strong bonds. Now, hydrogen bonds are more like using a Post-it note. You can stick a Post-it note to a piece of paper, you can pull it off, you can stick it back on, you can pull it off. It doesn't take a lot of energy. Hydrogen bonds are very important to living things because every bit of energy that a living thing needs, it has to produce. So if you have the ability to have some atoms or some molecules kind of attracted to each other through hydrogen bonds, and then it doesn't take a lot of energy to break those bonds, it gives an opportunity for the organism to have some interactions with molecules, but they're not high energy interactions. Covalent bonds occur when atoms overlap their outer shells. And when they overlap their outer shells, they share electrons. Nobody gets electrons, nobody gives up electrons, they're simply shared. Atoms may share one electron between them, that would be a single bond, two electrons, that would be a double bond, and occasionally atoms will share as many as 3 electrons, and that's called a triple bond. If the electrons across the atoms are shared equally, we say that that is a non-polar covalent bond. But if the electrons are arranged in the molecule so that there's a higher density of electrons in one place and a higher density of protons in another place, we say that that's unequal sharing of electrons, and those are polar covalent bonds. Now, when you break covalent bonds, you get your two atoms back. It's a lot like shaking hands with someone. When you're shaking hands with someone, you're connected to them, but when you ungrasp them, when you separate, everybody gets all their fingers back, they get their full hand back, there's no loss or gain of anything. Truly, the atoms have been sharing electrons. Now, here's an example of some elemental molecules. Hydrogen only has one electron in its outer shell. It will bind with a second one. Their electron shells will overlap. They'll share those 2 electrons. This particular hydrogen atom thinks it has 2 electrons. This one thinks it has 2 electrons. Everybody's happy. That's a single bond. They're only sharing 1 electron between them. If you break this bond, you get back 2 hydrogen atoms. Oxygen is another element that will form molecules. Now, if you look at oxygen, in its outer shell, it has 6 electrons. So it's looking for 2 more electrons to have a full outer shell. In this case, when oxygen overlaps, it actually shares 2 electrons with the other atom. Now, this is called a double bond because they're sharing 2 electrons. But again, this atom has 8 electrons in its outer shell. This atom has 8 electrons in its outer shell, and this sharing is what keeps these 2 atoms together. If you break this bond, you go back to 2 atoms of oxygen. Now, this is an example of a nonpolar bond where the electrons are shared equally. Hydrogen, again, looking for 1 electron for its outer shell. This is carbon. It's got 4 electrons. It's looking for 4 more. Now, if 4 hydrogens cozy up to it, each hydrogen can share 1 atom with the carbon. So the hydrogen thinks it's got its full share of electrons. And the 4 hydrogen atoms share their electron with the carbon, and now if you look at that carbon outer shell, it's got 8. So everybody's happy. And here you see another way to write this: carbon in the center and 4 single bonds, one with each hydrogen. This is nonpolar because there's no uneven distribution of protons or electrons. The electrons are all shared equally among all of the atoms in this molecule. Water, however, is a polar covalent bond because the electrons are not shared equally. Remember, oxygen has normally 6 electrons, so it's looking for 2 more. So in this case, 2 hydrogens cozy up to it. The hydrogens have their 2 electrons, and now oxygen has its 8 electrons. But look at the distribution. See how we've got more electrons up on this end of this molecule? And these hydrogens, their little protons, are kind of hanging out here without too much protection. So this means that the molecule has just a tiny, tiny bit of electrical charge. Not a real big heavy one, just a little tiny one. So this end of the molecule is just an itty bit negative, and this end and this end of the molecule are just the tiniest bit positive. Not strong, just a little bit. And this is what will contribute to hydrogen bonds we'll talk about in just a minute. So this is a polar covalent bond because you get a positive end and a negative end to the molecule that's formed. Unequal sharing. The other kind of strong chemical bond was the ionic bond. Now in this one, atoms lose or gain electrons. This is not like the handshake where you get everything back. If you were shaking hands here, you'd lose something in the process. So these atoms are going to deliberately lose electrons or gain electrons. Now as soon as they do that, they're no longer electrically neutral. They're either going to have more electrons than protons or more protons than electrons. So they become charged particles, and we call those charged particles ions. Now if something loses electrons, it's going to have more protons left behind, so that ion will have a positive charge. And we call those cations. Now it's easy to remember that cations are positively charged because there's a little plus sign right there in the middle of the word. If an atom gains electrons, it's going to have more electrons than protons. It's going to be negatively charged, and we're going to call that an anion, and that stands for a negative ion, anion. These things, when ions tend to get together, they tend to form crystals, and they are usually made of a metallic ion and a non-metallic ion, or metallic and non-metallic ions, and we refer to these things chemically as salts. Now here's an example of a very common salt, sodium chloride, table salt. Sodium only has 1 electron in its outermost shell. That electron is kind of lonely, and the protons of the nucleus here are pulling these 10 electrons in very, very tightly, but this 11th electron out here is just kind of out in the ozone a little bit. Chloride, on the other hand, it has 7 electrons in its outer shell. It is desperately looking for that 8th electron. This is a little bit like an old maid looking for a husband. Just anything will do. Any spare electron they can find, it will snag onto. Or this electron from sodium is kind of easily attracted over here to this chloride atom. Now when that happens, we're left with a sodium ion with a positive charge and a chloride ion with a negative charge. Opposites attract. Positive attracts negative. These things are stuck together. We have an ionic bond. Remember this picture I showed you a little earlier that showed the electron arrangements around the molecules? Notice that just a few electrons in the outer shell here. Down here we have more electrons as we're moving to that perfect 8. We can talk about the electronegativity of the atoms here. That is, how likely are they to give up electrons? How likely are they to pick up electrons? So Over on this end, where there's just one or two electrons in the outer shell, they have a low electronegativity. They're very, very likely to easily give up electrons. Down here on this end, we go to that higher electronegativity. These are looking for just one or two electrons to complete their outer shell. They accept electrons very easily. And of course, this last column over here has no electronegativity because they're electrically happy. They don't need any more electrons. So let's talk about hydrogen bonds. Hydrogen bonds occur between polar molecules because those polar molecules have areas that are a little more positive and areas that are a little more negative. These are very weak bonds that form between those positive and negative poles of the molecules. You see hydrogen bonds a lot in molecules that contain carbon and hydrogen, or nitrogen and hydrogen, because both carbon and nitrogen are a lot like water in that they don't share their electrons equally with hydrogen very often, and they can have those polar kinds of molecules. So here we see water molecules, and we know that the oxygen end is just a little bit negative and the hydrogen end is just a little bit positive, so we've got that weak attraction here. Weak attraction, weak attraction, weak attraction. If you've ever taken a balloon and rubbed it on your hair to make static electricity and then had the balloon stick to the wall, you know, it's stuck. You could pull it away pretty easily. You could restick it pretty easily. That's what hydrogen bonds are like. They just kind of keep the molecules attracted to each other without being very strong. It doesn't take much energy to break them. Now what's interesting is when you use water as a solvent, and you put ionically bonded compounds into water, they dissociate. We say they dissociate in aqueous solutions. Aqueous solutions are water solutions. And that's because the little bit of charge on the water will sort of get in between the positive and negative charges of the ionically bonded chemicals. As a result, we have positive ions in the solution and negative ions in the solution. And these solutions conduct electricity. So these kinds of solutions are called electrolytes, or these kinds of atoms are called electrolytes. So that's what all of an electrolyte is an electrically charged particle that will conduct electricity. Now, molecules are going to interact with each other, and we're going to have chemical reactions. All cellular work, anything a cell does, requires energy, and the cell has to make that energy. Energy cannot be created, nor can it be destroyed, but it can change form. So if you have mechanical energy, let's say you're riding your bike and so you're generating mechanical energy, your muscles are turning the wheels on the bicycle, your bicycle will roll, you'll get mechanical energy, but you'll also build up a little bit of heat friction as the tire hits the road. So you don't get necessarily, when you convert energy, you don't necessarily get all of the energy in the form you want. Electrons, remember, are energy, so we're going to be paying attention to where the electrons are because that's where the energy is in any of these chemical reactions. All those chemical bonds involve electrons. So chemical bonds are how we store energy. If we make bonds, think about pushing two Lego blocks together to make something bigger, you used energy. So whenever we make bonds, we store energy. If we break bonds, we have to release that stored energy. Sometimes we get light, sometimes we get heat, sometimes we make something move, but we get that energy back out. We don't always get all of the energy in the form we want it. Sometimes we get some energy byproduct we don't want, but the same energy that went into making the bond comes out when we break the bond. When we talk about chemical reactions, the things we're putting together are called the reactants, and the things we end up with are called the products. And we usually use this arrow to say that these things are going together and these things are coming out. So reactants yield products. In living things, most of the reactions that we need do not take place fast enough to sustain life. And so catalysts are special substances that can speed up chemical reactions. In living cells, these catalysts are called enzymes, and enzymes are all proteins. Now, when we have an enzyme involved, it will be written above the arrow because a catalyst is neither part of the reactants nor not part of the products. It doesn't enter into the reaction, it simply speeds it up. The catalyst comes away from the reaction totally unchanged. Oxidation reduction reactions are something we have to understand because these talk about how the electrons flow. These are sometimes referred to as redox reactions. Now, whenever you make or break bonds, somebody ends up getting some electrons out of the deal and somebody ends up losing some electrons in the deal. Whatever gains the electrons gains energy, because electrons are energy. And even though this sounds odd, this process is called reduction. If something loses electrons, then it loses energy. And this is referred to as oxidation. Now, to help you remember that, remember Leo Ger. Lose electrons, oxidation. Gain electrons, reduction. Lose electrons, oxidation. Gain electrons, reduction. Electrons by themselves are little bits of energy, and little bits of energy bouncing around can do damage. So it's safer if we always have an electron travel with a partner. And the most logical partner would be a proton, because that's a positively charged thing. An electron and a proton is a hydrogen atom. So we can tell whether things have been oxidized or reduced by looking at where the hydrogen is. So we have NAD, that's the oxidized form of the molecule. When you see NADH, it's the reduced form. The hydrogen being added indicates that it gained electrons. If it gains electrons, it's reduced. If we see it in this form, we know it's lost its hydrogen. It's lost electrons, so it has been oxidized. We divide chemical reactions up into whether they're making new bonds or breaking bonds. Synthesis reactions are the formation of large molecules from smaller molecules. Now, since you're putting things together, you're building something, that requires energy. So this kind of reaction is referred to as an endothermic reaction. Energy goes into it, endothermic. A way to depict this is to say small molecule A plus small molecule B equals large molecule AB. These kinds of reactions in living things are also referred to as anabolism. Now, most of these kinds of reactions can also be classified as dehydration or condensation synthesis because we get water as an end product of the reaction. If you have a small molecule that you want to stick another small molecule on, this small molecule is pretty happy by itself, and this small molecule is pretty happy by itself, so we have to do something to them, take something away from them so they'll want to stick to each other. If we can find an oxygen and a hydrogen, which is called a hydroxyl group on one, and a hydrogen on the other, we simply pull those out and make water, and we leave a place where the two molecules now want to stick to each other. So we have made water, dehydration or condensation, and water is a nice little end product to make because the body or the cell has a lot of different ways that it can handle water. It can excrete it, it can use it in other ways. We need a lot of water in organisms anyway, so it's a very safe end product. It's non-toxic, it's good to use. The reverse of synthesis is decomposition. Decomposition, like it sounds, is simply breaking larger molecules into smaller ones. Because we're breaking bonds, we're going to be releasing electrons, we'll be releasing energy. These are called exothermic reactions, energy out. So if we have a large molecule, AB, and we break it down into A plus B, we have done a decomposition reaction. In living things, this is referred to as catabolism. Now, once again, we've got to have some reason for this big molecule to want to exist as two independent molecules. And we can use water to help us break the bond. So these are called hydrolysis reactions. Again, you've got your big molecule. This molecule is very happy being stuck together like this. And if we're going to break it somewhere, it's going to want to stick back together at that point because it needs something to cover up the broken places. So if we have water hanging around, when we break the bond, we can break that water down into that hydroxyl group and that hydrogen group, and we can stick those in between the places where we're breaking. Now we have a complete smaller molecule that doesn't want to react with anything, and another smaller molecule that doesn't want to react with anything. Most chemical reactions in the body are kind of combination reactions. They're what we call exchange reactions. That is, the components of the reactants break apart and recombine to form new products. So it's kind of like AB plus CD. The A and the D recombine and the C and the B recombine, and you make new products from the reactants. Because you're breaking bonds and reforming bonds, it depends exactly on the nature of the exchange reaction if overall you make more energy or overall you use more energy. So the energy release depends exactly on the reactions. Now most reactions in cells are reversible, so you'll see the arrow going in two directions, and what makes it drive one way or the other may be something simple like the presence of a particular enzyme or a temperature or a particular pH. Now we've mentioned water as being an important molecule here. Water is a polar covalent molecule, and it has this ability to turn into hydrogen ions and hydroxyl ions, that OH with the negative. So in some ways it can act sort of like an ionic compound, but it also comes apart pretty easily so that we have those little bits and pieces when we're breaking bonds to put and heal the break a little bit. Water is the most abundant substance in life. Cells are 50 to 99% water, depending upon the type of cells. And water is a very unique substance. It has a lot of special properties. First of all, it's cohesive. Those hydrogen bonds make it stick together. And this cohesiveness gives water something called surface tension. If you've ever put water on a tabletop, you'll notice that it beads up, and you can even put your finger in one of those drops of water and drag it around. That's the surface tension, or the cohesiveness of water. Water is also an excellent solvent. It dissolves more substances on Earth than anything else. And for molecules to come into contact with each other, they need to be in some sort of medium where they can bump into each other. A liquid medium is a good way to do that. So water dissolving things allows molecules to come in contact with each other for chemical reactions. Water freezes at 0 degrees centigrade, turns solid. It vaporizes at 100 degrees centigrade, that is, it becomes steam, so it stays liquid over one of the widest ranges of anything else, any other element or any other compound, in terms of maintaining a particular form of matter. Now that's important if you are basically a liquid organism and you're relying on the fluidity for chemical reactions to occur. It's nice if your liquid stays liquid and doesn't solidify at too low a temperature or vaporize at too low a temperature. Water can absorb high quantities of heat. If you have a swimming pool or you go out to the beach, you know, we've had a lot of hot days before that water is really warm because it takes a long time to warm up water. But in the fall, when we start to get cooler air temperatures, the water stays warmer longer because water gives up heat very slowly. So it doesn't change temperature very rapidly. Again, if you're mostly made of water, that's a good thing. And as we have seen, water is a prime participant in many chemical reactions, either being produced as the result of a synthesis reaction or being used to break bonds in a hydrolysis reaction. Solutions occur when molecules are uniformly dispersed in something. We talk about the solvent as the dissolving medium. In most instances, our solvent is water, and the dissolved substance is the solute. So if you have sodium chloride solution, for example, water is the solvent and sodium chloride is the solute.